Did you know there are clouds in space that are larger than entire solar systems? Clouds so vast that light takes years to travel from one end to the other, and within them, at temperatures near absolute zero, stars are being born at this very moment. Hello, and welcome to another journey through the universe. I hope you're comfortable wherever you are, perhaps relaxing after a long day, or seeking a moment of pause to contemplate something greater than our daily concerns. This is a space we create together to explore the wonders of the cosmos, so make yourself at home. If you're enjoying this type of contemplative content about the universe, consider subscribing to the channel and leaving a like on this video. It really helps me continue bringing these cosmic journeys to you, and shows me that it's worth investing time in this kind of more reflective exploration of the universe. Now, take a deep breath with me and let's begin our exploration. Feel the air entering and leaving your lungs, that same air that carries elements which once inhabited the depths of space, which were forged in the hearts of ancient stars. Today I want to take you on an extraordinary journey through nebulae, these cosmic nurseries where stars are born. We'll talk about places where time moves differently, where creation happens on scales so grand that our human minds can barely comprehend them. Have you ever wondered where stars come from? Not just as an abstract scientific question, but really stop to contemplate this mystery. When we look at the night sky and see those points of light twinkling gently, we're observing the final result of a process as beautiful and complex as the birth of life on Earth. Imagine for a moment that you could travel through space, not in a noisy and uncomfortable spacecraft, but as pure consciousness, capable of crossing light years in seconds, of witnessing events that last millions of years as if they were instants. In this imaginary journey, you would encounter regions of space that are simultaneously nurseries and graveyards, places where the end of one story becomes the beginning of another. These regions have a poetic name that perfectly matches their ethereal nature, nebulae. The word comes from Latin and means cloud, but what kind of cloud would this be? They're not the familiar clouds we see in Earth's sky, made of water vapor and ice crystals. They're cosmic clouds, immense structures composed of gas and dust that extend across distances so vast that light takes years to traverse them. But here's what fascinates me most about nebulae. They are literally the nurseries of stars. Within these apparently empty and silent clouds, a cosmic drama unfolds constantly. It's a drama of fundamental forces, gravity, pressure, temperature, electromagnetism, all dancing together in a complex choreography that results in the birth of new suns. Have you ever thought that perhaps we ourselves were born from a nebula? Not metaphorically, but literally. The elements that make up your body, the carbon in your muscles, the iron in your blood, the calcium in your bones, all were forged in the interior of stars that were born in nebulae billions of years ago. And when those stars reached the end of their lives, they scattered these elements throughout space, creating new nebulae that would give birth to new stars, planets, and eventually to you. It's a circular story, a cosmic narrative where each ending is a new beginning. And this story is happening right now, as we speak. Somewhere in the depths of space, a nebula is slowly collapsing under its own gravity, compressing hydrogen until it becomes so hot and dense that nuclear fusion begins, and a new star ignites its first light. Allow yourself for a few moments to forget daily concerns, schedules, obligations. Let's explore these cosmic nurseries together, understand how they work, discover the different types that exist, and perhaps, in the process, find a new perspective on our own existence. After all, if we are children of the stars and stars are born in nebulae, then each of us carries within us the ancestral memory of these cosmic cradles. Close your eyes for an instant and imagine the void. Not the void of a dark room or an empty box, but the true void of interstellar space. Now, in this apparent emptiness, begin to populate it mentally with something almost imperceptible, hydrogen atoms floating alone, separated by immense distances like microscopic islands in an ocean of darkness. This is the basic material of nebulae, hydrogen, the simplest and most abundant element in the universe. One proton, one electron, nothing more. It seems like little, doesn't it? But it's from this fundamental simplicity that all cosmic complexity develops. It's as if the universe were a minimalist composer, creating extraordinary symphonies from a single note. Have you ever wondered how these solitary atoms, scattered throughout vast space, manage to come together to form structures as majestic as nebulae? This is where one of nature's most subtle yet powerful forces comes into play: gravity. Gravity is a curious force. Unlike magnetic or electric force, which can both attract and repel, gravity only knows how to do one thing: attract. It's always gentle, never violent, but absolutely relentless. Each hydrogen atom in space exerts a minuscule gravitational force on all other atoms, no matter how distant they may be. Imagine these atoms as shy people at a giant party. At first, everyone is scattered, maintaining a respectful distance from each other. But there's something irresistible that attracts them to one another, an attraction so subtle they barely notice it, but which never stops acting. Slowly, almost imperceptibly, they begin to approach each other. This process of gravitational attraction happens on timescales that challenge our human understanding. We're talking about millions, sometimes hundreds of millions of years. For us, who live a few decades, it's difficult to imagine such slow processes. It's like trying to observe the growth of a mountain. We know it's happening, but we need a temporal perspective very different from ours to truly understand. As hydrogen atoms approach each other, they begin to form increasingly larger clusters. These clusters, in turn, exert a stronger gravitational attraction, pulling even more material toward them. It's a positive feedback process. The more mass accumulates, the stronger the attraction becomes, the faster additional material is collected. But hydrogen isn't alone in this cosmic dance. Mixed with it, we find microscopic grains of dust, solid particles composed of heavier elements like carbon, silicon, iron, and oxygen. These grains are like cosmic seeds, remnants of stars that existed long ago and which, upon dying, scattered their processed elements throughout space. Cosmic dust plays a fascinating role in this process. Although it represents only about 1% of a nebula's total mass, it's fundamental to what happens next. Dust grains act as catalysts, facilitating chemical reactions that would be impossible in empty space. They also absorb radiation from nearby stars, protecting the surrounding gas and allowing it to cool. You might be wondering, but where exactly does this happen? Nebulae don't arise from nothing, in completely empty regions of space. They have specific cradles, places where conditions are favorable for this accumulation process to begin. Often, nebulae are born in the spiral arms of galaxies, regions where interstellar gas is naturally denser due to density waves that traverse the galactic structure. Other times, they're created by stars themselves. When a massive star explodes as a supernova, it sends shock waves through surrounding space, compressing interstellar gas and creating the initial conditions for a new nebula's formation. There are also planetary nebulae, a misleading name as they have nothing to do with planets. They arise when intermediate mass stars, like our Sun, reach the end of their lives and expel their outer layers, creating bright shells of ionized gas around the remaining stellar core. Each type of nebula has its own personality, its own visual and physical characteristics. Some shine with vibrant colors, intense reds, ethereal blues, ghostly greens. Others are dark, visible only as silhouettes against the starry background. All, however, share this fundamental quality. They are places where the universe's raw material reorganizes itself, where the simple becomes complex, where potential transforms into reality. There's something deeply poetic in the way nebulae paint space with colors we rarely see on Earth. When we contemplate images captured by great telescopes, the Hubble, the James Webb, the Spitzer, we're presented with a color palette that seems to come from a dream, crimson reds that pulse like the heartbeats of a cosmic heart, ethereal blues that remind us of deep waters from another world, emerald greens that float like luminous ghosts in the darkness. But have you ever wondered where these colors come from? Why does one nebula shine in red while another glows in blue? The answer leads us to one of physics' most elegant dances, the interaction between light and matter. Imagine you're holding a special lamp, one that emits not just visible light, but the entire electromagnetic spectrum: ultraviolet rays, X-rays, radio waves. This lamp is a young, hot star newly born in the heart of a nebula. Its light travels through space in all directions, carrying energy at different wavelengths. When this light encounters hydrogen atoms in the nebula, something magical happens. The ultraviolet photons from the star are so energetic that they can strip electrons from hydrogen atoms, a process called ionization. It's as if light were a key that unlocks atomic structure, freeing electrons to wander through space. But nature doesn't like imbalances. Eventually, these free electrons are recaptured by atomic nuclei, returning to their original orbits. And when this happens, they emit light, but not just any light. Each chemical element has its unique luminous signature, its own fingerprint in the electromagnetic spectrum. Hydrogen, when its electrons return to their original orbits, emits a specific red light, what astronomers call the H-alpha line. This is why many nebulae glow with that characteristic red, so intense it seems to pulse even in static photographs. It's literally the light of hydrogen singing its atomic song. But nebulae are more complex than that. They also contain other elements: helium, oxygen, nitrogen, sulfur, each contributing its own colors when ionized. Oxygen produces greens and blues, nitrogen adds subtler reddish tones, helium contributes golden yellows. It's as if each nebula were a chemical orchestra, with each element playing its specific note in the symphony of light. There are different types of luminous nebulae, each with its own illumination mechanism. Emission nebulae are like giant cosmic neon lamps. They produce their own light through the ionization and recombination of atoms. Reflection nebulae, on the other hand, are more like ethereal mirrors. They don't produce their own light, but reflect and scatter light from nearby stars. Reflection nebulae have a distinctive visual characteristic. They're typically blue. This happens for the same reason our terrestrial sky is blue. Blue light is scattered more efficiently than other colors by small dust particles. It's a phenomenon called Rayleigh scattering, and it's fascinating to think that the same physical process that colors our terrestrial sunsets also paints these distant cosmic clouds. Have you ever noticed how the quality of light changes throughout the day? In the morning, we have that golden, soft light. At midday, an intense white light. At sunset, reddish and orange tones. Nebulae also have their own cosmic times of day, determined by the age and temperature of the stars that illuminate them. Young, very hot stars produce abundant ultraviolet radiation, creating bright and colorful emission nebulae. Older, cooler stars don't have enough energy to ionize surrounding gas, resulting in subtler reflection nebulae. And when stars are being born, still wrapped in their cocoons of gas and dust, they may be completely invisible in optical light, revealing themselves only in infrared. But there's a third type of nebula that might seem contradictory: dark nebulae. These don't shine at all. In fact, they do the opposite. They are clouds so dense with gas and dust that they completely block light from stars behind them, creating dramatic silhouettes against the illuminated background of the Milky Way. Dark nebulae are perhaps the most mysterious and contemplative of all. When we observe them, we're literally seeing the absence of light, the negative space of cosmic art. They remind us that the universe isn't just about brightness and spectacle, but also about subtlety, patience, and the transformative power of darkness. There's something deeply human in our response to nebular colors. Perhaps it's because these colors awaken ancestral memories, echoes of a time when our distant ancestors were just stardust floating in a primordial nebula. Or perhaps it's simply because beauty, wherever we find it, connects us with something greater than ourselves. There are moments in nature when change happens so gradually it's almost imperceptible, and others when it occurs with sudden intensity that transforms everything. In the heart of a nebula, both types of change coexist in a fascinating cosmic dance. For millions of years, nothing seems to happen, just gas and dust floating silently through space. Then, almost as if the universe decided it's time, the process of stellar formation begins with surprising intensity. Imagine a dewdrop forming slowly on a leaf at dawn. At first, it's just imperceptible moisture in the air. Gradually, water molecules aggregate one by one until suddenly there's a visible drop, then a larger drop, and finally it becomes too heavy and rolls down the leaf. Star formation in nebulae follows a similar pattern, but on spatial and temporal scales that challenge our imagination. The trigger for this gravitational awakening can come from various sources. Sometimes It's the shock wave from a distant supernova that crosses the nebula like a stone thrown into a calm lake, creating density ripples that propagate through the gas. Other times, it's stellar winds from nearby massive stars, streams of charged particles that push and compress nebular material. But perhaps most intriguing is when the nebula itself decides it's time to awaken, when its own accumulated gravity reaches a critical point. It's as if it reached a critical mass of cosmic self-awareness and said, "Now is the time to create." When a region of the nebula begins to collapse gravitationally, the initial process is almost imperceptible. Hydrogen atoms, which were separated by vast distances, begin to approach each other. It's a movement so slow that if you could observe in real time, it would be like watching paint dry, but multiplied by millions of years. As the gas compresses, something interesting happens with its temperature. You might think that, when compressed, the gas would cool. After all, that's what happens when we release air from a tire. But in space, the rules are a bit different. Initially, the gas actually cools as it expands and contracts slowly. But there's a turning point, a critical moment when compression becomes irreversible. This point is known as Jeans collapse, named after physicist James Jeans, who first mathematically described the phenomenon. It's the moment when the cloud's gravitational energy overcomes the thermal pressure trying to disperse it. From this point on, there's no going back. The cloud is destined to collapse until it forms a star. Now the process accelerates dramatically. What took millions of years to begin happens in just a few 100,000 years, a blink of an eye in cosmic terms. As the gas collapses, it heats up due to compression. It's the same principle that heats a bicycle pump when you use it vigorously, but amplified to monumental scales. The collapsing cloud develops a complex structure. At the center, a dense, hot core forms, what will eventually be the star. Around it, material continues falling toward the center, creating currents and turbulence in the gas. It's like a cosmic hurricane, with material being sucked toward the center in complex spiral patterns. But not all the material from the original cloud directly participates in star formation. Much of it forms what we call a protoplanetary disk, a flattened, rotating structure around the forming protostar. It's in this disk that, eventually, planets can form. Our own solar system was born this way, about 4.6 billion years ago, in a disk of gas and dust around the young sun. Have you ever observed a whirlpool forming when water goes down a sink drain? There's something hypnotic about the way water spirals inward, accelerating as it approaches the center. The gravitational collapse of an interstellar cloud has a similar quality, but in 3 dimensions and with forces that can create not just one, but dozens or hundreds of stars simultaneously. During this process, the protostar doesn't yet shine with its own light. It's wrapped in a dense cocoon of gas and dust that absorbs all the light it produces. To an external observer, the region would appear as a dark nebula, a silhouette against the starry background. But inside this cocoon, extraordinary events are occurring. The temperature in the protostar's core continues rising. First, a few hundred degrees, then thousands, eventually tens of thousands of degrees. As temperature rises, hydrogen begins to behave differently. Electrons are stripped from atoms by thermal energy, creating a plasma, a state of matter where atomic nuclei and electrons exist separately. And then, when the core temperature reaches about 10 million degrees Celsius, something truly magical happens. Nuclear fusion begins. Hydrogen nuclei begin to fuse, forming helium and releasing enormous amounts of energy in the process. It's the moment of stellar birth, when a protostar becomes a true star, igniting its first light. This moment is one of the most dramatic in the universe. In a matter of days or weeks, the radiation pressure produced by nuclear fusion sweeps away the cocoon of gas and dust that surrounded the protostar. For the first time, the new star's light emerges and illuminates the surrounding nebula, revealing the beauty that was hidden in darkness. There's something deeply theatrical about the way stars are born in nebulae. Like actors emerging from the wings to take the stage, they appear suddenly where there was only darkness before, bringing drama, light, and color to regions that seemed empty and silent. But unlike human theater, where plays have clearly defined beginnings, middles, and ends, the cosmic theater of nebulae is a continuous performance, where each act is simultaneously a finale and a premiere. When a new star ignites for the first time, it doesn't do so discreetly. The event is announced by an explosion of radiation that completely transforms the surrounding nebula. It's as if someone suddenly turned on all the lights in a dark theater, revealing not just the stage but all the ornate architecture that was hidden in the shadows. The ultraviolet radiation from the newly born star immediately begins ionizing hydrogen in the surrounding nebula, creating a bright region known as an H2 region. This region grows like a bubble of light expanding through the gas, illuminating structures that were previously invisible. It's a process that can take thousands of years to complete, but the result is spectacular. Have you ever had the experience of being in a dark room and lighting a candle? First, there's just the small flame, then gradually the light spreads, revealing nearby objects, then distant furniture, finally illuminating the entire room. The ionization of a nebula follows a similar pattern, but the candle is a star and the room can be light years in diameter. As the ionized region expands, it encounters variations in the nebular gas density. Some areas are denser, others more rarefied, creating complex patterns of light and shadow. This is where nebulae acquire their characteristic shapes. They're not random structures, but cosmic sculptures carved by the interaction between stellar radiation and the non-uniform distribution of matter. Some of the most impressive shapes are created when multiple stars are born simultaneously in the same region. Each star creates its own ionization bubble, and when these bubbles meet and interact, they produce even more complex structures. Imagine multiple stones being thrown simultaneously into a calm lake. The waves propagate, meet, interfere with each other, creating unique patterns on the water's surface. But newly born stars don't affect only the surrounding gas through their radiation. They also produce stellar winds, streams of charged particles that flow constantly outward from the stellar surface. These winds are especially intense in young, massive stars, creating cavities and bubble-shaped structures in the nebula. The result are the magnificent formations we see in nebular images: pillars of gas and dust extending for light years, spherical cavities carved by stellar winds, ionization fronts advancing like luminous waves through the interstellar medium. Each nebula is unique, a cosmic work of art created by the specific interaction between its stars and their environment. There's something almost organic about how these structures develop. Gas pillars resemble giant corals or rock formations sculpted by erosion. Cavities look like cells or bubbles. Shock fronts move like waves on a beach. It's as if the universe followed aesthetic patterns we instinctively recognize, even on scales vastly different from our daily experience. One of the most fascinating characteristics of active nebulae is that they frequently contain stars at different stages of formation. While some regions already house mature stars that brightly illuminate surrounding gas, other areas still contain protostars wrapped in their dark cocoons, waiting for their moment to emerge. It's like observing a garden where some flowers have already bloomed completely, while others are still buds promising future beauty. This temporal diversity creates extraordinary visual richness. In a single nebula, we can see the intense red of H2 regions, the ethereal blue of reflection nebulae, the dark silhouettes of dense globules where future stars are forming, and the greens and golds of more exotic elements ionized by particularly hot stars. But perhaps the most poetic aspect of nebulae is that they are fundamentally transitory. A typical nebula has an active life of only a few million years, an extraordinarily brief period in cosmic terms. During this time, it produces a generation of stars, is transformed by its own creation, and eventually disperses, its delicate structures gradually being undone by the same stellar winds that helped create them. It's a cycle of creation and destruction that mirrors many natural processes we know on Earth, but on scales of time and space that challenge our understanding. A nebula is born, flourishes in spectacular beauty, creates a family of stars, and then slowly dissolves into the interstellar medium, leaving only its stellar children as witnesses to its past existence. And so the cosmic theater continues, with new actors constantly emerging, new plays being performed, new dramas unfolding in the depths of space. Each nebula is simultaneously an end and a beginning, a conclusion and an opening, an epitaph for what was and a promise of what's to come. If we could trace a family tree of stars, we would discover family stories as complex and intertwined as those of any human dynasty. But unlike terrestrial genealogies, where each generation is clearly distinct from the previous one, stellar lineages extend across billions of years, and ancestors leave material inheritances to their descendants, literally sharing their atoms through time and space. Think for a moment about the most familiar star to us, the Sun. Our Sun wasn't the first star to shine in this region of the galaxy. Long before it was born, about 4.6 billion years ago, other stars lived their complete lives in this cosmic neighborhood. Some of these ancestral stars were giants, masses dozens of times greater than the current Sun, which burned their nuclear fuel quickly and ended their lives in spectacular explosions. When these giant stars exploded as supernovas, they didn't simply disappear. They scattered throughout surrounding space all the elements they had created during their lives, carbon forged in their cores over billions of years, oxygen produced in their inner layers, iron created in the final moments before explosion. These elements mixed with the primordial hydrogen that permeated space, enriching it and preparing it for the next generation of stars. This is how our Sun inherited its chemical diversity. Although composed mainly of hydrogen and helium, it also contains traces of dozens of other elements, the material inheritance of stars that died long before it was born. And when the Sun eventually dies, it will also bequeath its processed elements to future generations of stars. It's a chain of inheritance that extends from the universe's beginnings to a distant future we can barely imagine. But nebulae aren't just nurseries for individual stars. They're frequently birthplaces of entire stellar families. When a giant nebula collapses, it rarely forms just one star. Instead, fragmentation of the collapsing gas results in the formation of stellar clusters, groups of dozens, hundreds, or even thousands of stars that are born approximately at the same time and in the same region. These stellar clusters are like cosmic siblings. They share not only the same age, but also the same basic chemical composition, having formed from the same reservoir of gas and dust. It's fascinating to think that somewhere in the galaxy, there may be thousands of stars that are literally sisters to our Sun, born in the same primordial nebula. 4.6 billion years ago? Have you ever wondered if these sister stars are still out there? The answer is probably yes, but they've scattered across the galaxy over billions of years. The original stellar cluster where the Sun was born dispersed long ago, its member stars following independent orbits around the galactic center. It's like a large family reunion that ended long ago, with relatives scattered across the country, following their own lives. Some stellar clusters, however, managed to stay together for a long time. Globular clusters, for example, are ancient, dense structures containing hundreds of thousands of stars in a relatively small region of space. These clusters are like stellar cities, where stars are so close to each other that the group's collective gravity keeps them united for billions of years. Within these stellar families, there's fascinating diversity. Depending on each star's initial mass, they evolve at very different rates. The most massive stars burn their fuel quickly and die young in just a few million years. Medium-mass stars, like the Sun, have much longer lives, shining steadily for billions of years. And the smallest stars, red dwarfs, can live for trillions of years, longer than the universe's current age. This means that, in an ancient stellar cluster, we can see stars at different stages of evolution. Some have already died and become white dwarfs or black holes. Others are in their final life stages, swelling to become red giants. And still others are in the prime of life, shining serenely as the Sun does today. It's like observing a human family where, due to some temporal magic, we could simultaneously see grandparents as they were in youth, parents in their middle age, and children growing up. Each star in the cluster is a window into a different moment of stellar evolution, allowing us to understand not just how stars live, but how they die. And when stars die, they frequently create new nebulae. A solar mass star, like the Sun, will end its life by expelling its outer layers, creating a planetary nebula, a bright shell of ionized gas that slowly expands through space. More massive stars explode as supernovas, creating supernova remnant nebulae, complex, energetic structures that can shine for thousands of years after the original explosion. These second-generation nebulae are different from the primordial nebulae where stars were born. They're composed mainly of heavy elements, carbon, oxygen, neon, iron, created inside stars during their lives. When these nebulae eventually mix with the interstellar medium, they enrich the gas with elements essential for forming rocky planets and eventually life. It's a majestic cycle of creation, life, death, and rebirth that repeats continuously in the galaxy. Each generation of stars is richer in heavy elements than the previous one. Each new nebula is more chemically complex than its predecessors. It's as if the universe were a poet who continuously improves his vocabulary, adding new words and expressions to each poem he writes. There's something deeply comforting in this cosmic continuity. It means that nothing is truly lost in the universe. It just transforms. The atoms that make up your body have passed through multiple generations of stars, have been part of ancient nebulae, have witnessed the birth and death of entire worlds. You are literally made of stardust, not just metaphorically, but in an absolutely literal way. There are moments when science becomes pure poetry, and perhaps nowhere is this more evident than when we try to understand the colors of nebulae. When we look at these stunning images captured by space telescopes, we're seeing much more than just beauty. We're seeing the very chemistry of the universe expressing itself through light. Imagine you could see colors that don't exist on Earth, hues that only appear under the extreme conditions of deep space. Nebulae offer us exactly that, a color palette that has no parallel in our terrestrial experience. Colors that tell stories about temperature, density, chemical composition, and physical processes occurring on unimaginable scales. Let's begin with red, perhaps the most characteristic color of emission nebulae. This deep, intense red isn't just a color, it's literally the luminous signature of hydrogen, the simplest and most abundant element in the universe. When an electron in hydrogen falls from a high-energy orbit to a lower one, it emits a photon with a very specific wavelength, 656.3 nanometers, which we perceive as crimson red. But have you ever stopped to think about the extraordinary precision of this color? It's not just any red, it's a specific red determined by the fundamental laws of quantum mechanics. It's as if every hydrogen atom in the universe were a musician playing exactly the same note in perfect tune, creating a cosmic symphony of red light. The green in nebulae has an even more fascinating story. For a long time, astronomers observed a bright green line in the spectrum of many nebulae, but couldn't identify which element produced it. They even created a name for the hypothetical element, nebulum. Only decades later did they discover it wasn't an unknown element, but oxygen under conditions so extreme they had never been observed on Earth. This green light is produced by oxygen atoms that have lost 2 electrons, doubly ionized oxygen. Under Earth's normal conditions, these oxygen ions would recombine almost instantly with free electrons. But in the near-perfect vacuum of nebulae, they can remain ionized for long periods, creating this ghostly green color that exists nowhere else. The blue in reflection nebulae has a completely different origin. It's not produced by atomic emission, but by light scattering, the same process that makes our sky blue. Small dust particles in nebulae scatter blue light from nearby stars more efficiently than other colors, creating these ethereal blue regions that seem to float like luminous ghosts in space. It's extraordinary to think that the same physical process that colors our terrestrial skies also paints these distant cosmic clouds. There's a deep continuity in nature's laws. The same rules that govern light behavior in Earth's atmosphere also apply in the vast expanses of interstellar space. But nebular colors aren't just scientifically interesting, they also evoke deep emotional responses. There's something about those intense reds that awakens a sense of power and energy. The ethereal blues suggest mystery and transcendence. The ghostly greens evoke the supernatural, the otherworldly. Perhaps these emotional responses aren't coincidence. Maybe, at some deep level, we recognize these colors as part of our cosmic heritage. After all, the elements that make up our bodies were forged in stars that were born in nebulae like these. Perhaps there is, encoded in our DNA, an ancestral memory of these primordial colors. Modern imaging technologies allow us to see nebulae at wavelengths invisible to the human eye. The Spitzer telescope showed us nebulae in infrared, revealing hidden structures in cosmic dust. The Chandra X-ray Observatory allowed us to see hot winds from young stars carving cavities in nebulae. Radio telescopes showed us spectral lines of complex molecules forming in the cold of space. Each wavelength reveals a different facet of the same nebula. It's like examining a jewel under different types of light. Each illumination reveals new aspects of its beauty and structure. A nebula that appears simple and uniform in visible light may reveal intricate and complex structures when observed in infrared. But there's something special about the colors we can see with our own eyes, even if through telescopes. These are colors our evolutionary ancestors could have seen if they had the technology to observe deep space. They're colors that speak directly to our human visual perception, without need for false coloring or technical translation. When we contemplate these nebular images, we're participating in one of the most fundamental acts of cosmic connection possible for our species. We're literally capturing photons that have traveled for tens or hundreds of light years through space, carrying information about processes that occurred long before our birth, in places so distant they challenge our capacity for understanding. And yet, through the universal language of light and color, these distant regions communicate with us. They tell us about their temperature, their composition, their age, their history. They show us that, despite the vast distances and timescales involved, we're part of the same cosmic story, a story written in the colors of infinity. If nebulae were just uniform clouds of gas and dust, however beautiful they might be, they wouldn't have the power to fascinate that they exercise over us. What really captures our imagination are their structures, pillars extending for light years, perfectly sculpted spherical cavities, shock fronts propagating like waves frozen in time. These formations aren't random accidents, but the result of complex physical processes acting as cosmic architects. Think for a moment about the pillars of the Eagle Nebula, perhaps the most famous nebular structures ever photographed. These majestic pillars, extending several times the size of our solar system, aren't static structures. They're dynamic, constantly being sculpted by radiation from the young, hot stars that were born in the same nebula. The process is fascinating in its complexity. The intense ultraviolet radiation from newly born stars ionizes surrounding gas, creating an ionization front that moves through the nebular material. But this front doesn't move uniformly. It encounters regions of different density as it advances. Where the gas is denser, the front moves more slowly. Where it's more rarefied, it accelerates. It's like water flowing around obstacles in a stream. Water finds the path of least resistance, going around rocks and creating turbulence patterns downstream. Similarly, the ionization front goes around the denser regions of the nebula, creating these spectacular columnar structures we call pillars. But there's a poetic irony in this process. The same stars that create the beauty of the pillars are also gradually destroying them. The radiation that sculpts these structures also slowly erodes them, like wind and rain wearing away terrestrial rock formations. It's a process of simultaneous creation and destruction, where beauty exists precisely because it's transitory. Have you ever observed clouds forming and dissipating in the sky? There's something hypnotic about the way they constantly change, never remaining exactly the same for long. Nebular structures follow a similar pattern, but on much longer time scales. A pillar that takes thousands of years to form can be eroded in a few 100,000 years, fast in cosmic terms, but an eternity to us. Another type of fascinating structure are stellar bubbles, almost perfectly spherical cavities, sculpted by winds from individual stars. When a young, massive star is born, it doesn't just emit radiation, but also produces a stellar wind, a constant flow of charged particles moving at speeds of thousands of kilometers per second. This stellar wind pushes away surrounding gas, creating an expanding cavity. It's like blowing a soap bubble, but a bubble made of ionized gas that can be dozens of light years in diameter. The bubble's edge, where stellar wind meets nebular gas, forms a dense, bright wall that we can observe telescopically. These stellar bubbles are extraordinary natural laboratories for studying plasma physics and magnetohydrodynamics. The conditions within them, temperatures of millions of degrees, extremely low densities, intense magnetic fields, are impossible to replicate in terrestrial laboratories. They offer us unique windows into physical processes that occur only under space's extreme conditions. But perhaps the most dramatically beautiful structures are those created when a massive star reaches the end of its life. When a star with more than 8 times the Sun's mass exhausts its nuclear fuel, it doesn't die gently. Instead, it explodes in a supernova, an explosion so energetic it can temporarily shine brighter than an entire galaxy. The shock wave from this explosion propagates through the interstellar medium at speeds of thousands of kilometers per second, compressing and heating the gas it encounters along the way. The result are supernova remnant nebulae, complex, filamentary structures that can persist for tens of thousands of years after the original explosion. These nebulae have a particular, almost ghostly beauty. Their delicate filaments and lace-like structures resemble cosmic spiderwebs, but made of gas heated to millions of degrees. They're simultaneously monuments to stellar death and seeds for new star birth. As the supernova's shock wave can compress nearby gas clouds, initiating new episodes of stellar formation. There's a deep symmetry in this process. The violent death of an old star can catalyze the birth of a new generation of stars. It's as if the universe had found a way to transform endings into beginnings, to convert conclusions into prologues. Nebular structures also teach us about the importance of turbulence in the cosmos. For a long time, we thought of space as a calm, ordered environment, but modern observations reveal it to be surprisingly turbulent. Stellar winds, supernova explosions, intense radiation, all these phenomena create turbulence in the interstellar medium, and this turbulence plays a crucial role in structure formation. It's turbulence that creates the complex patterns we see in nebulae, the twisted filaments, irregular cavities, regions of variable density. Without turbulence, nebulae would be much simpler and less interesting structures. Turbulence adds complexity, beauty, and diversity to the universe. And so, these cosmic architects, radiation, stellar winds, shock waves, turbulence, work continuously to create and recreate the structures we admire in nebulae. They're artists who never rest, always sculpting new forms, always experimenting with new configurations, always transforming the simple into complex, the uniform into diverse. When we look at a nebula through a telescope, we're doing something extraordinary that we rarely pause to contemplate. We're traveling through time. The light we capture began its journey to us decades, centuries, or even thousands of years ago. We are cosmic archaeologists, excavating the past through photons that have crossed the interstellar void to tell us stories of remote epochs. Consider for a moment the Orion Nebula, one of the closest and most studied star-forming regions. It's located approximately 1,344 light-years from Earth. This means the light we see today left the nebula around the year 680 of our era, when the Byzantine Empire was at its height, when Arabs were beginning their great conquests, when Mayan and Aztec civilizations flourished in the Americas. It's a dizzying perspective, isn't it? While human civilizations were being born and dying, while empires rose and fell, while human art, science, and philosophy evolved through the centuries, these photons were traveling silently through space, carrying information about processes occurring in a distant nebula, but cosmic archaeology goes much further than that. Some nebulae are so distant that their light has taken millions of years to reach us. When we observe these nebulae, we're seeing how they were when Earth was still young, when the first hominids were walking through Africa, when continents had different configurations than today's. There's something deeply humbling in this realization. All of human history, from the first cave paintings to space flights, from the invention of writing to the internet, all of this happened during the time it took light from some distant nebulae to reach us. We are simultaneously observers of the cosmos and participants in its history, witnesses to a spectacle that began long before we existed. Nebulae are also messengers of processes that occur on completely different timescales from our experience. A star can take millions of years to form within a nebula. The nebula itself can exist for tens of millions of years before dispersing. To us who live a few decades, these processes seem eternal and immutable, but they're in constant change, just on a temporal scale, slow, we can't directly perceive it. It's like trying to observe a tree's growth. If you look at a tree for a few minutes, it will seem completely static. But if you could compress decades of observation into a few seconds, you'd see a dynamic organism growing, adapting, responding to seasons. Similarly, if we could accelerate our temporal perception, we'd see nebulae as vibrant, dynamic structures, constantly reforming and evolving. Astronomers have developed ingenious techniques to study these temporal changes. By comparing observations of the same nebula made decades apart, they can detect movements and changes that would be imperceptible on human timescales. It's like creating a time-lapse movie of cosmic processes, revealing the dynamic nature of structures that seemed static. Some of the most fascinating discoveries come from studying nebulae at different evolutionary stages. It's like studying a forest where you can simultaneously see seeds germinating, young trees growing, mature specimens at their peak, and old trunks decomposing. Each nebula represents a different moment in the life of these star-forming regions. The youngest nebulae are often dark and cold, visible only as silhouettes against the starry background or through infrared observations. They're like cosmic seeds, full of potential but not yet blossomed. Within them, protostars are slowly forming, still years or decades away from igniting their first lights. As nebulae evolve and their stars begin to shine, they become more visible and colorful. This is the most spectacular phase of a nebula's life, when it glows with all colors of the electromagnetic spectrum, when its structures are most defined and dramatic. It's cosmic adolescence, a period of intense activity and dazzling beauty. Eventually, nebulae age. Their most massive stars explode as supernovas. Their stellar winds disperse remaining gas. Their delicate structures are gradually eroded. It's the final phase of nebular life, when they slowly dissolve back into the interstellar medium, leaving only their stellar children as witnesses to their past existence. But even in death, nebulae are generous. The gas they return to the interstellar medium is enriched with heavy elements created in their stars. This enriched material will become part of future generations of nebulae, which in turn will form stars even richer in heavy elements. It's a process of progressive enrichment that has occurred throughout cosmic history. Have you ever thought that we can literally see this enrichment process happening? Nebulae in different parts of the galaxy, formed at different epochs, have slightly different chemical compositions. The oldest are composed almost entirely of hydrogen and helium. The most recent contain detectable amounts of heavy elements, oxygen, carbon, iron, created by previous generations of stars. It's like reading a chemical history book of the universe. Each nebula is a page in this book, recording the galaxy's state at the moment of its formation. The oldest pages tell us of a simpler universe, composed almost entirely of the lightest elements. The most recent pages reveal a universe that has become progressively more complex and chemically diverse. And we, human observers in the 21st century, are privileged to live at a time when we have the technology to read this cosmic book. We are perhaps the first species in Earth's history capable of understanding our connection with these distant structures, of recognizing that we are products of the same cosmic evolutionary history that created nebulae. Imagine for a moment that you could visit the universe's most advanced laboratory, a place where the fundamental laws of physics are tested under conditions impossible to replicate on Earth, where chemical elements are created from nothing, where nature's most basic forces operate on grandiose scales. You wouldn't need to travel to an advanced alien civilization to find such a laboratory. It's right here, in our own galaxy, spread throughout the nebulae that dot interstellar space. Nebulae are, fundamentally, laboratories of creation, places where the universe continuously experiments with new ways of organizing matter and energy. Within them, processes that would take billions of years under terrestrial conditions happen continuously, creating not just stars, but also complex molecules, organic compounds, and even the basic building blocks of life. Have you ever wondered where the chemical elements that make up your body were created? The answer is surprisingly poetic. They were forged in the hearts of stars that were born in nebulae. And when those stars died, they were scattered through space to become part of new nebulae. It's a cycle of creation and recycling that intimately connects your existence with these distant cosmic cradles. Hydrogen and helium, the lightest elements, were created in the first moments after the Big Bang. But all the heavier elements, the carbon in your muscles, the oxygen you breathe, The iron in your blood, the calcium in your bones, all were created inside stars. The process is called stellar nucleosynthesis, and it's literally cosmic alchemy in action. Inside a star's heart, temperatures are so high, tens of millions of degrees, that atomic nuclei can overcome their mutual electric repulsion and fuse. Starting with hydrogen, stars gradually build heavier elements. Hydrogen fuses to form helium. Helium fuses with hydrogen to form lithium and beryllium, and so on, climbing up the periodic table. It's a process that requires extreme conditions and immense time. A star like the Sun takes billions of years to convert just a small percentage of its hydrogen into helium. More massive stars can create elements up to iron in their cores, but this requires even higher temperatures and more intense pressures. It's as if each star were a cosmic factory, working patiently to create the chemical diversity that makes complexity, and eventually life, possible. But nebulae aren't just the nurseries where these stellar factories are born. They're also the places where the products of these factories are processed and redistributed. When a massive star explodes as a supernova, it not only scatters the elements it created during its life, but also subjects them to even more extreme conditions during the explosion. During the seconds or minutes of a supernova explosion, temperatures can reach billions of degrees, conditions so extreme that even heavier elements can be created. This is how elements like gold, platinum, and uranium are forged in the universe. These precious metals we value so highly on Earth are literally children of ancient stellar explosions. But there's another fascinating aspect of nebulae as laboratories. They're also places where complex molecules can form. You might think interstellar space is too cold and empty for interest in chemistry, but reality is surprisingly different. Astronomers have already identified more than 200 different types of molecules in interstellar space, including some surprisingly complex ones. In dense, cold regions of nebulae, atoms can aggregate on microscopic dust grains. The surface of these grains acts as a catalyst, allowing atoms to combine into molecules in ways that would be impossible in empty space. It's like having billions of tiny chemical laboratories scattered throughout a nebula, each experimenting with different atomic combinations. Some of the molecules found in space are surprisingly familiar: water, ammonia, methane, carbon dioxide. Others are more exotic: complex alcohols, organic acids, even amino acids, the building blocks of proteins. It's as if the universe were experimenting with the chemical ingredients necessary for life, long before planets like Earth existed. There's something deeply inspiring in the realization that nebulae are laboratories where life's ingredients are constantly created and refined. When planets eventually form from the material of these nebulae, they inherit not just basic elements, but also complex organic molecules that can serve as seeds for biological processes. It's possible that life on Earth didn't begin with simple molecules that gradually became more complex, but with relatively complex molecules that already existed in the material from which the solar system formed. Perhaps nebulae are not just nurseries of stars, but also nurseries of life itself. The extreme conditions in nebulae also allow unique physical processes to occur. Magnetic fields can be amplified to intensities millions of times greater than anything we can create on Earth. Particles can be accelerated to near-light speeds. Plasma waves can propagate across light-year distances. These processes aren't just scientific curiosities, they have practical implications for our understanding of physics. Many phenomena we observe in nebulae can only be understood by invoking more exotic aspects of modern physics: relativity, quantum mechanics, field theory. Nebulae are natural laboratories where these theories are tested under conditions we could never artificially replicate. For example, the jets of material that some young stars eject can extend for light years and move at speeds of hundreds of kilometers per second. Studying these jets helps us understand how magnetic fields can channel and accelerate ionized matter, knowledge that has applications in controlled nuclear fusion and space propulsion. Similarly, shock waves propagating through nebulae teach us about how energy and momentum are transferred through tenuous media. This understanding is crucial for modeling everything from space, weather affecting our satellites to seismic wave propagation through Earth. There's something deeply satisfying in realizing that these distant cosmic laboratories are constantly expanding our fundamental understanding of the universe. Each new observation of a nebula is potentially an opportunity to discover something new about how nature works on its most grandiose scales. There exists an entire universe of beauty and complexity that remains completely invisible to our unaided eyes. For thousands of years, humanity looked at the night sky and saw only a handful of nebulous stars, diffuse patches that were minor curiosities compared to bright stars and wandering planets. We had no idea we were looking at some of the cosmos' most grandiose and important structures. Imagine trying to understand a symphony by hearing only the highest notes, or trying to appreciate a painting by seeing only red colors. For a long time, our view of the nebular universe was similarly limited. We saw only visible light, a small fraction of the electromagnetic spectrum, and even this light was filtered and distorted by Earth's atmosphere. The revolution began when we developed the ability to observe the universe at wavelengths invisible to our eyes. First came radio observations, revealing that the empty space between stars was filled with hydrogen-emitting radio waves 21 centimeters long. Then came infrared, ultraviolet, X-ray observations, each revealing aspects of nebulae that were completely hidden in visible light. Have you ever had the experience of putting on glasses for the first time and suddenly seeing details of the world you didn't know existed? Multispectral astronomy was like giving glasses to all of humanity, allowing us to see the universe with a clarity and richness of detail our ancestors couldn't imagine. In infrared, nebulae that appeared dark and empty in visible light suddenly revealed intricate structures and intense activity. Cosmic dust, which blocks visible light, is heated by stellar radiation and re-emits this energy in infrared. It's like using thermal vision to see through fog. Suddenly, regions that seemed empty revealed themselves to be full of forming protostars. The Spitzer Space Telescope, operating in infrared, transformed our understanding of nebulae. It showed us that many regions that appeared static in visible light were actually dynamic centers of stellar formation. Protostars still wrapped in their dust cocoons became visible for the first time. Delicate structures of warm dust were revealed in extraordinary detail. But it was in ultraviolet that some of the most dramatic discoveries were made. Young, hot stars emit most of their energy in ultraviolet radiation that's completely absorbed by Earth's atmosphere. When we finally managed to observe nebulae in ultraviolet from space, we discovered a universe of activity that was completely invisible from the ground. The Hubble Space Telescope, with its ability to observe from near ultraviolet to near infrared, revolutionized our view of nebulae. Its images became iconic not just for their stunning beauty, but for the scientific richness they revealed. Structures that were just diffuse patches in ground-based telescopes were resolved into detailed pillars, complex shock fronts, and systems of jets and outflows. But perhaps even more revealing were X-ray observations. X-rays are produced by the universe's most energetic processes, gas heated to millions of degrees, particles accelerated to relativistic speeds, intense magnetic fields. X-ray observatories like Chandra showed us that nebulae are permeated by extremely hot gas, heated by winds and explosions from their most massive stars. It's like discovering that a tranquil garden is actually full of invisible activity, insects flying, roots growing, complex chemical processes occurring in the soil. Nebulae, which seemed like relatively calm regions in the visible spectrum, revealed themselves to be filled with energetic activity when observed in X-rays. Radio observations opened another fascinating chapter. Beyond hydrogen's 21 cm line, radio telescopes detected hundreds of spectral lines from complex molecules. We discovered that interstellar space is an active chemical laboratory, where complex organic molecules are constantly being created and destroyed. Some of these molecules are surprisingly familiar: water, ammonia, methanol. Others are more exotic, like polycyclic aromatics, PASE, that may be precursors to even more complex organic compounds. It's like discovering that empty space is actually a rich chemical soup, teeming with ingredients necessary for biological processes. The combination of observations at multiple wavelengths created a new way of seeing nebulae, not as static objects, but as dynamic, multi-layered systems. Each wavelength reveals processes operating at different temperatures, densities, and energy scales. It's like having multiple senses to perceive the same phenomenon, each contributing unique information. But perhaps most exciting is that we're still in the early stages of this observational revolution. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is revealing details of nebulae we could never see before. Future observatories promise to expand our vision even further, observing at even more exotic wavelengths. There's something deeply humbling in realizing how limited our previous view of nebulae was. There's also something deeply exciting in realizing that each new technological window we open to the universe reveals complexities and beauties we didn't suspect existed. It makes you wonder, what other marvels are out there, waiting only for us to develop the right instruments to see them? When we contemplate modern nebular images, colorful compositions, combining data from multiple telescopes and wavelengths, we're seeing something no human eye could see directly. We are like cosmic artists, using technology to paint portraits of the universe that are simultaneously scientifically accurate and aesthetically dazzling. And perhaps that's what most fascinates me about these windows to the invisible. They show us that the universe is even more beautiful and complex than we could imagine. Each new observational capability reveals not just new scientific phenomena, but new forms of cosmic beauty. It's as if the universe had infinite layers of magnificence, each waiting to be discovered. There are moments in science when a single discovery completely changes our perspective on our own existence. One of these moments occurred when we realized that we're not just passive observers of nebulae, we are products of them. Every atom in our body, except the simplest hydrogen, was forged in the interior of stars that were born in ancient nebulae. We are literally made of stardust. But this connection goes far beyond poetry. It's fundamental, intimate, inescapable. The iron flowing in your veins was created in the core of a massive star that lived and died billions of years ago. The calcium in your bones was synthesized during the final moments of a supernova explosion. The oxygen you breathe was produced by nuclear fusion in the hearts of multiple generations of stars. Think about this for a moment. Your existence is only possible because stars were born, lived, and died in nebulae long before the solar system existed. You are the final product of billions of years of cosmic alchemy, a conscious being capable of contemplating the very processes that created you. It's a realization that should fill us simultaneously with humility and wonder. When our solar system formed 4.6 billion years ago, it was born from a nebula that was already enriched with heavy elements from previous generations of stars. This nebula, sometimes called the primordial solar nebula, was a complex mixture of primordial hydrogen and helium with heavier elements scattered by the deaths of ancient stars. Imagine this primordial nebula as a cosmic library, where each type of atom was like a book written by a different star. Carbon atoms told the story of medium-mass stars in their final stages. Ion atoms narrated the dramatic moments of supernova explosions. Gold atoms whispered about collisions between neutron stars. And we, modern humans, are like conscious librarians, capable of reading these atomic stories. But there's another fascinating aspect of this connection. Not only are we made of material from ancient nebulae, but we're also capable of studying and understanding modern nebulae. It's as if the universe had developed a way to know itself through conscious beings like us, who emerge from the very cosmic dust we study. Have you ever wondered if there are other beings like us in distant nebulae? Statistically, it's almost certain. With billions of stars being born in nebulae throughout the galaxy, and with many of these stars probably forming planetary systems, it's likely that some of these planets have developed life, and some of these living beings have evolved intelligence. Perhaps, somewhere in a distant nebula, other beings are looking in our direction, contemplating our own region of the galaxy as we contemplate theirs. Perhaps they too have discovered they're made of stardust. Perhaps they too feel this same deep cosmic connection we feel when we contemplate nebulae. There's something deeply comforting in this possibility. It means we're not alone, not just in the sense that there may be life elsewhere, but in the deeper sense that we may share a common origin and similar perspective on the universe. We are all children of stars, all products of the same cosmic alchemy. The discovery of planets orbiting other stars, exoplanets, has made this connection even more tangible. Many of these exoplanets formed from protoplanetary disks in distant nebulae, using the same basic process that created our own solar system. When we observe a nebula where stars are currently being born, we're potentially seeing nurseries of future worlds and perhaps future living beings. This perspective fundamentally changes how we see our position in the universe. We're not external visitors observing an alien cosmos. We're native participants, natural products of the same processes we study. When a nebula creates new stars, it's potentially creating future observers who will one day contemplate other nebulae. It's a deeply poetic cycle. Nebulae create stars, stars create heavy elements. Heavy elements combine to form planets, planets develop life, life evolves consciousness, consciousness contemplates nebulae. The universe has become conscious of itself through us. But there's also a fascinating temporal dimension to this connection. The atoms in our body aren't just old, they're truly archaic. Some of the hydrogen atoms in your water may have formed in the first minutes after the Big Bang. Some of the carbon atoms in your cells may be more than 10 billion years old, created in stars that died when the galaxy was still young. You are a walking collection of cosmic history. Every atom in your body has a biography extending billions of years and trillions of kilometers. Before becoming part of you, these atoms floated through interstellar space, were part of nebulae. Perhaps were incorporated into other stars, possibly were part of other planets or even other forms of life. It's a perspective that should give us a sense of deep connection not just with the cosmos, but with all life on Earth. All living beings share the same cosmic heritage. We're all made of the same recycled stardust. The tree in your yard, the cat sleeping in the window, the microorganisms in the soil, we all share common stellar ancestors. And when we eventually die, our atoms will return to the cosmic cycle. They'll become part of soil, atmosphere, other living beings. Eventually, some of them may even return to space, perhaps to become part of future nebulae and future stars. We are part of a cosmic recycling cycle that extends from the universe's beginning to its most distant future. There's something simultaneously humble and grand in this realization. Humble, because it shows us we're temporary products of processes much larger than ourselves. Grand, because it shows us we're integral parts of cosmic history, intimately connected with the universe's most magnificent structures. As we contemplate the present of nebulae, these magnificent structures that dot our galaxy like cosmic gardens in full bloom, it's natural to wonder about their future. Where do all these stories of creation and transformation go? What will the universe be like when current nebulae have completed their life cycles? And what new forms of beauty and complexity await in the cosmic eras to come? The future of nebulae is intimately linked to the future of the galaxies that house them. Our own Milky Way is on a collision course with the Andromeda Galaxy, an event that will occur in approximately 4.5 billion years. When these two galaxies meet, it will be one of the most grandiose spectacles in the local cosmos, not a violent collision, but a slow, majestic gravitational dance that will take billions of years to complete. Imagine what will happen to nebulae during this galactic encounter. Density waves created by gravitational interaction will compress gas clouds in both galaxies, triggering intense bursts of stellar formation. New nebulae will be born from cosmic turbulence, glowing with even more intense colors as young massive stars illuminate surrounding gas. It will be an era of cosmic renaissance when our galaxy will experience a second youth. But this near future is just the beginning of the story. Looking even further ahead, we can contemplate how nebulae will evolve over tens of billions of years. As the universe ages, the supply of primordial gas to form new stars will gradually be exhausted. Nebulae will become increasingly rare, each representing an increasingly precious event of stellar creation. There's something melancholic but also beautiful in imagining the universe's last nebulae, solitary structures glowing against the growing darkness of the cosmos, like the last flowers blooming in a garden at autumn's end. These final nebulae will be composed almost entirely of heavy elements, products of trillions of years of stellar evolution. They'll form stars that will be fundamentally different from today's stars. metal-rich objects that could sustain planetary systems of unimaginable complexity. Have you ever thought about what life will be like on those distant future worlds? Planets formed from material so rich in heavy elements could sustain forms of life based on much more complex chemistry than ours. Perhaps civilizations will arise that consider it normal to have oceans of complex hydrocarbons, atmospheres rich in organic compounds, continents made of exotic minerals that barely exist on current Earth, but even these future nebulae will eventually come to an end. As the universe continues expanding and cooling, there will come a time when there's no longer enough gas to form new stars. The last nebulae will disperse, their stars will follow their solitary lives, and the era of stellar formation will come to an end. This doesn't mean the story of nebulae will end completely. Even in a very ancient universe, occasional cataclysmic events may still create new opportunities for stellar formation. Collisions between white dwarfs can produce supernovas that compress remaining gas. Mergers between black holes can eject material that eventually condenses into new clouds. Nature is creative and persistent. It will find ways to continue creating beauty even under the most unlikely circumstances. And there's another fascinating aspect of nebulae's future: the possibility that advanced civilizations might learn to create their own artificial nebulae. If intelligent beings survive for billions of years and develop unimaginably advanced technologies, perhaps they could collect dispersed interstellar gas and organize it into new regions of stellar formation. Imagine civilizations that are literally architects of nebulae, capable of designing and building stellar nurseries with artistic precision. They could create nebulae with specific shapes, desired colors, programmed to produce particular types of stars. It would be the ultimate form of cosmic art, living sculptures made of gas and light, designed to evolve and change over millions of years. But perhaps the most profound aspect of nebulae's future is that they teach us about the cyclical nature of cosmic existence. Even when current nebulae disperse and their stars die, the elements they created will persist. These elements will become part of even larger structures, perhaps entire galaxies composed mainly of heavy elements, or forms of matter organization we can't yet imagine. The universe may be finite in age, but it seems infinite in creativity. Each cosmic era brings new forms of beauty and complexity. Today's nebulae are just one chapter in a much larger story of cosmic organization and reorganization. When they're gone, other forms of magnificence will take their place. There's something comforting in this long-term perspective. It means the beauty we admire in nebulae isn't something transitory and meaningless, but part of a broader pattern of cosmic creativity that extends indefinitely into the future. We are privileged witnesses to a particular moment in this continuous story of creation, and who knows? Perhaps our own descendants, whether biological or artificial, organic or digital, will still be around in unimaginably distant futures, contemplating new forms of cosmic beauty we can't even conceive today. Perhaps they'll look back at our era of natural nebulae with the same poetic nostalgia with which we look at the universe's first stars. The future of nebulae is, ultimately, a story about the persistence of cosmic creativity. No matter how much the universe changes, no matter how different physical conditions become, nature will continue finding ways to create beautiful and complex structures. Today's nebulae are our inheritance from the cosmic past and our gift to distant futures. We've reached the end of our journey through nebulae, but in a way we've also arrived at a new beginning. Because understanding nebulae, these stellar nurseries, scattered throughout space's depths, is fundamentally understanding our own origin and our place in the grand cosmic narrative. It's discovering that we're not strangers in an alien universe, but native children of processes extending across billions of years and trillions of kilometers. When you look at the night sky tonight, your perspective will be different. Those points of light are no longer just distant stars. They're sisters to the sun, born perhaps in the same cosmic nurseries, forged by the same fundamental processes. And in the dark regions between stars where your eyes see nothing, you now know magnificent structures exist, nebulae where new stars are being born at this very moment, where creation continues its tireless work. There's a poetic irony in the fact that, to truly understand our terrestrial home, we had to travel imaginatively to the galaxy's confines. To understand where we came from, we had to study places so distant that their light takes decades or centuries to reach us. To appreciate our own existence, we had to contemplate processes operating on timescales that make our individual life seem like the blink of an eye. But perhaps this is the deepest lesson of Nebulae, that scale and meaning aren't necessarily related. Yes, we're small compared to interstellar vastnesses. Yes, our existence is brief compared to stellar life cycles. But we're also extraordinary products of billions of years of cosmic evolution, beings capable of understanding and appreciating the very processes that created us. Think about this. You're made of atoms that were literally cooked inside stars, elements that were dispersed through space in cataclysmic explosions, matter that spent billions of years floating in the cosmos immensities before aggregating to form the planet where you were born. And now, through an improbable chain of biological evolution and cultural development, you're capable of consciously contemplating this extraordinary history. Nebulae teach us that the universe isn't just a collection of separate objects occupying empty space. It's an interconnected system where each part influences all others, where the past shapes the present and the present prepares the future. The atoms in your body have passed through multiple generations of stars. The water you drink may contain hydrogen that formed in the first. Minutes after the Big Bang, you are simultaneously a product and participant in cosmic history. There's also something deeply democratic in Nebulae's message. They show us that creation isn't the privilege of some special places in the universe. It happens continuously, everywhere conditions are favorable. Each nebula is a center of cosmic creativity. Each star-forming region is a laboratory where the universe experiments with new configurations of matter and energy. And we, human observers of the 21st century, have the extraordinary privilege of being the first species on Earth capable of understanding this cosmic perspective. Our ancestors looked at the sky and saw mysteries. We look at the sky and see family. We see our heritage, our origin, our intimate connection with the cosmos' broader history. But this understanding also brings responsibilities. If we're truly children of stars, products of billions of years of cosmic evolution, then perhaps we have an obligation to preserve and continue this history of growing complexity and beauty. Perhaps our role in the cosmos is to be conscious guardians of universal creativity, beings capable of appreciating, understanding, and perhaps even participating in the continuous creation of beauty and meaning. Nebulae also teach us cosmic patience. The processes they represent operate on timescales that challenge our immediate understanding. A star can take millions of years to form, billions of years to live, and its influence can persist for billions of years after its death. It's a perspective that can help us see our own life and concerns in a broader context. This doesn't diminish the importance of our individual existence. On the contrary, it can increase it. If we're products of such grandiose and lasting processes, if we carry in our bodies the history of cosmic creation, then each moment of consciousness is extraordinarily precious. We are temporary forms of organization through which the universe becomes conscious of itself. When you go out tonight and look at the stars, remember you're looking at your extended cosmic family. Those distant lights are your stellar sisters, born from the same fundamental processes that eventually led to your existence. And in the dark regions between them, invisible nebulae are working patiently to create the next generations of stars, planets, and perhaps even forms of life. You're not an alien visitor in this universe, you're a natural product of its most fundamental processes. You're stardust that organized itself in such a way as to contemplate its own origins. You're the universe becoming conscious of itself, a temporary but precious form of cosmic organization. And perhaps this is Nebulae's most profound message, that beauty, complexity, and meaning emerge naturally from the cosmos' most basic processes. The universe isn't just a collection of matter and energy moving blindly through space. It's a creative system that continuously generates new forms of organization, complexity, and eventually consciousness. You are living proof that the universe is not only capable of creating beauty, but also beings capable of appreciating that beauty. And in that act of appreciation, in that moment of cosmic contemplation, something extraordinary happens. The universe completes itself, finding in you a mirror through which it can contemplate its own magnificence. Thank you for accompanying me on this journey through stellar nurseries. May it inspire in you a new appreciation for both the vast cosmic structures and the precious singularity of your own conscious existence. And now, as we return from this imaginary cosmic voyage to the present moment, to the place where you're sitting or lying, to the immediate reality of your breathing and your thoughts, I leave you with a final question to contemplate. If you are truly made of stardust, if you carry in your body the history of billions of years of cosmic evolution, what does this mean for how you choose to live your precious and brief life in this singular moment of the universe's history?